Hello everyone. Today I will be discussing our paper entitled Sparse Orthogonal Matching Pursuit by Parameter Estimation for Integrated Sensing and Communication, authored by myself, Dương Ngọc Sơn, along with my colleague Đinh Thị Thái Mai from University of Engineering and Technology in Vietnam, Ngô Khắc Hoàng from Linköping University in Sweden, and Van-Linh from National Chung Cheng University in Taiwan. Our research addressed a critical challenge in the development of next generation wireless system, particularly in the context of integrated sensing and communication, which play an important role in 6G network. ISAC promises to enhance spectrum efficiency, reduce hardware redundancy, and improve communication performance by integrating sensing functionality. However, accurate parameter estimation such as Angle of Arival remain a significant difficulty due to issues like channel sparsity, noise, and high pilot overhead. The core idea of our work is to leverage the shared AOA between sensing and communication channels to improve estimation accuracy. So first, let's look at the figure 1a. The figure 1a here is our system model. It includes an ISAC-BS, an UE, and some target. At first, the ISAC-BS send and collect echo signal for environment sensing, and at the same time the UE send pilot in the uplink connection to for channel estimation. In this paper, we assume that the way of communication part is the same with the sensing part. And in the figure 1b here is the beam spec sensing channel. And you can see that the beam spec sensing channel is not completely spare. It poses a 2D direct current structure which span multiple grades, preventing a single atom from capturing the entire power of a given part. And based on this structure, we will introduce a novel OMP algorithm for sensing channel estimation. This table compare our methods to conventional OMP algorithm. You can see that both algorithms start with a atom selection step. It calculates the correlation between residual Rn and the atom in sensing matrix omega m, and to the maximum value C at the position and map. Compared with conventional OMP, our method have a extra step to exploit the channel structure. We put multiple atoms into a set J prime. Though atom would belong to the main loop of one given part. And since we choose multiple atoms, we have to evaluate its contribution to power of one part. And the sum weight of all part atoms in one step would be 1, and weight of each atom is based on its correlation. We have another step here to evaluate contribution of each atom in previous step. After that, we update the superset and estimate the path gain by weighted linear least square instead of linear least square like conventional OMP. And finally, we update the residue and go back to the first step. After that, we refine the coarse sensing and communication parameter by introducing an refinement methods. The refinement process here is performed simultaneously for both sensing and communication function when the spare attribution occur find that they have the same AOA. The least square cos function for the joint K here is Q joint, and otherwise it estimates separately with two different cos functions at QC and QF. And this is our result. In figure 2, we use successful recovery probability and mean square error of AOA to compare our method with some baseline. The main result is the RP of novel OMP improved as the number of subcarrier increase. It's shown in figure 2a. And our novel OMP method performance in low NR increase in low NR scenario is better than the traditional S rate. It is shown in figure 2b. You can see that here. And RMSE in the AOA CRLB is 2.5 times better than the non-AOA CRLB at the same NR level. And this improvement arrived from leveraging information from both communication and sensing subsystem. And this concludes also true in theory. We have a corollary. It said that considering a system consisting of two subsystems, for example, an uplink communication system S1 and a sensing system S2, if the subsystem say a common parameter theta, then the lower bound of CR theta is lower than elemental lower bound of theta, assuming that they operate independently, saying no parameter. This claim is proved in our paper. So, in conclusion, this paper presents a novel approach to channel attribution in millimeter wave scenario by leveraging sensing information from the ISAC system and to improve the accuracy of both sensing and communication function. We formulate ISAC processing at a spare signal recovery problem and propose a novel OMP-based method for sensing parameter estimation. In addition, we introduce a estimator and analysis demonstrating that sensing and communication functions can mutually enhance overall channel estimation performance, particularly when the sensing target serves as a scatter point.